Alright, grade 11, so we're moving on to something called the sine rule. Now, once we delve into examples, we'll see why we need the sine rule. So let's just look at what the sine rule says and where the proof comes from. And then when we look at examples, I'll explain exactly why the need for this arose. Now, first of all, the sine rule is true in any triangle ABC. So notice there's not a single right angle in this triangle. It's true in every triangle. And what does the sine rule say? Well, first of all, let's just quickly remember that if this is vertex A, that would be called angle A, and we label a triangle by labeling the fact that the side opposite angle A will be called baby A, and the side opposite angle B would be called baby B, and the side opposite angle C would be called baby C. Now with that in mind, the sine rule says that A, side A, over sine of the angle opposite it will be exactly the same as side B divided by side of the angle opposite it, and that's exactly the same as C over sine of the angle opposite it. Now that's called the sine rule. It's on your formula sheet, but there is a second version, and the second version of the sine rule is that you could flip everything over. You could also say that sine of angle A over the side A is the same as sine of angle B over the side B is the same as sine of angle C over C. Now why do we need two different versions? Well, they're exactly the same thing. I've just flipped everything around. However, if I'm using the sine rule to solve for a side, I use the first version, because in this first version your sides are at the top, so it makes it easier to solve an equation if what you're looking for is at the top of the equation. I use the second format if I'm trying to solve for an angle, because again it's easier to solve for something that's at the top of an equation. Now that might look a little bit weird. We never actually work with all three of these equal to things. So what you'll find is we land up choosing, maybe I'm working with, side B, and so I choose that part of this to work with. But the idea is that all three of these fractions will always be equal. Now let's look at the proof, because it's actually a pretty easy proof. And in an exam, they won't ever ask you to prove all three fractions are equal. They will choose two. So let's pretend they asked you to prove that B over sine angle B is equal to C over sine angle C. Now hopefully they've drawn the triangle for you. If they haven't drawn the triangle for you, notice if you're talking about the angles of B and C, I always put those vertices at the bottom of my picture. Now this proof is examinable, but it's fairly simple. So what is our proof? Well, as with most proofs, it begins with a construction. So I'm going to construct my perpendicular height, and I'm going to call it AD. So that means straight from vertex A, I'm going to drop a perpendicular height down to BC. I'm going to call this point D. Now often we call this baby H for perpendicular height. Some people then get confused with H for hypotenuse, so you can just leave it being called AD if you prefer. Now in order to go further, let's just quickly label our triangle. This side here, the side of CB, would be called baby A, this would be called baby B, and this would be called baby C. Now what I've done by dropping this perpendicular height is create some right angle triangles. And the first right angle triangle is this blue one, and it involves the angle at vertex B. So because it's a right angle triangle, we can use normal trig and just simply look at what is the definition of sine B. Well, sine angle B, by definition, is the opposite side, which you can call AD or you can call H for height, over the hypotenuse, and the hypotenuse in this blue triangle is C. Now if I multiply by C on both sides, I get C times sine of angle B is equal to H. Now that's not the only right angle triangle that we've created with this perpendicular height. We have triangle ACD. So if we go and look in that triangle at the value of sine angle C, now because it's right angled, you can use normal trig. And the definition of sine is opposite, which is again this height, or you could say AD, divided by the hypotenuse, which in this case is b. So in a similar way, I'm going to multiply by b on both sides, so this becomes b times sine of angle c is your height. Now what this has created is it's created one expression for h, which is c sine b, and another expression for h, which is b sine c. Now these are the same h's, so I'm going to say, but hang on one moment, h and h are equal to each other because it's the same height. Now what that means is that c times sine of angle b, which is your first expression for h, must be exactly the same thing as your second expression for h. Now in an exam, I would just write, therefore, b over sine angle b is the same thing as c over sine angle c, because that's what you wanted to prove. Okay, but how did that work out? So I'm just going to show you on the side. I probably wouldn't include this in an exam because it's not necessary, but let's just quickly go and figure out what caused that to happen. So we had c times sine angle b is equal to b times sine angle c. Now depending on what they ask you to prove, you can either keep the sine of the angles on the top, or you can keep the c and the b on the top. Now that is why both of these versions of the sine rule exist, because all I'm doing is manipulating this now, and you can manipulate it in whatever way you want. So if I wanted to keep the sides at the top, I would basically divide by sine of angle b on both sides. Now what that does is it causes the sine angle b to cancel, and so I get c equals b times sine angle c all over, and I've got the sine of angle b at the bottom. Now in exactly the same way, I'm going to divide by angle c on both sides, and so my sine of angle c cancels on the right hand side, and so I actually get what they wanted, because I get c over sine angle c is equal to b over sine angle b, which is written the opposite way around to what they gave, but it doesn't matter. So what I've written in grey here is not something I would write in the exam. Remember, this proof is examinable, so you pretty much learn it off by heart, but you don't want to be wasting time showing manipulations that really don't have to. So in summary, this part here, my construction, my setting up of the signs in the two different triangles, and my equating, and then my conclusion, that's what I would like to see when we ask you to prove the sine rule. Okay, now what does this actually mean? How does this actually help me? Let's go have a look at examples, because I think that kind of really brings to life what the sine rule does. So let's look at example 1. Now the first thing to just point out, I'm afraid I made a typo here when I was doing this. This should be 11 centimeters. Now one first thing to state immediately, always look first if this is right angled. If it's not, don't even go anywhere near sine, cos and tan's definition. So I've just written that as a note to myself. That's the first thing I always check. Where are my right angle triangles? And if there are right angle triangles, then I go and highlight them, because those are the only triangles you can actually use the definition of sine, cos and tan in. So why did we need the sine rule? Well, if you look at this triangle isn't right angled. And the moment something isn't right angled, there's absolutely no ways to do anything. You can't use Pythagoras' theorem, and you can't use the definitions of trig. So if this question is asking for the angle at B, I can't even do sum of angles in a triangle because I don't know two angles. So how, once we've done all three rules that we're going to do, what is the trigger that I should think, oh my word, this is the sine rule? Well, first of all, you have to be given, the sine rule works in pairs, because the sine rule is always about an angle and its opposite side. So you have to be given one of the pairs. So you need an angle and its opposite side. You have to know that in order to proceed. So again, I've written that as a note, because once we've done all of our rules, you've got to be able to recognize what's useful to you. So number one thing with the sine rule, if you're given an angle and its opposite side, you're looking good, because it means you know one of those ratios that we were working with. Now notice in this example, I've been given one of the sides. So if I've been given another side, it means I can work out the angle opposite it. And that also works vice versa. If you're given the angle, you could work backwards to the side opposite that angle. So you basically have to be given one pair, and then you have to be given something else. So I've written myself a note there that says I have to either be given two sides and one angle, because then I have one pair and an angle, so I can work out its opposite pair, or I have to be given two angles and one side, and then I can work out a second side. Again, that might be too much information, so let's have a look at this example. Now, just before we set up the sine rule, I just want us to note one last thing. The bigger the angle, the bigger the side opposite that angle. So the moment I see 16 centimeters here, that's bigger than 11 centimeters. So that means that angle B must be bigger than angle A, because it's opposite a bigger side. The bigger the angle, the bigger the side must be opposite it. Now, what does the sine rule say? The sine rule says two things. We can either start with a side at the top or an angle at the top. Now, this first part of this question says solve for angle B, which means I would personally immediately start with sine of angle B. Put your angle at the top because that's what you're looking for. Now, the sine rule says sine of angle B divided by the side opposite it, which is 16, is going to be equal to sine of any one of the other angles, and I only have one angle here, so 42, divided by the side opposite it, which is 11. Now all I need to do is isolate the sine of angle B so I can solve my equation. So I'm going to multiply by 16 on both sides so that my 16s cancel, and so I get sine of angle B, and you must keep all these decimals. I often use a dot 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 because I can just use the answer button on my calculator. Now this is where it gets a little bit tricky, because this is now a sine equation. Now, sine equations have two different answers. My first answer is I just do shift sine. And if I do shift sine of my answer, don't forget to use the answer button so you don't have to type in decimals, I get 76,73 degrees rounded off to two decimal places. But every sine equation has two solutions. So if I do 180 minus that, because that's the second way to solve a sine equation, I get 103,27 degrees. So where does this come from? Just to remind myself, this comes from 180 minus 76,73. Okay, now which one of these is right? Well, let us look at the picture. Is this an obtuse angle at B, or is it an acute angle? Because that's the only difference, and they've drawn me a picture so I can tell. Now I can see that this is obtuse because it clearly is bigger than 90 degrees, and so we can't be talking about the 76. We must be talking about this simply because the picture says that angle B is obtuse. So this does just take looking at the picture. Now, I'm going to be honest with you, it's very rare that you have to find the second solution. Most of these are just going to be shift sine, and that's your answer, because we try not to be too mean in these questions. So a little bit of mean one to start with, but I think it's important to realize that there actually are two possibilities, and our picture narrows down the option for us. Right, so that's angle B down. So angle B is now 103. I always like to fill in what I figured out because it might help me. Now I'm running out of space here, so I'm going to divide myself into a little box over here to continue, because I'm now asked for the length of AB. Now AB is this side here. Now I can't use Pythagoras as it isn't right angled. However, that side is opposite angle C. Now I don't know angle C, but never forget that an angle, the third angle in a triangle, is always possible to find, simply because you can use the sum of angles in a triangle. So if I do 180 minus my 103.27 minus my 42, and you don't show working like that, you can just do it on your calculator, I get 34,73 degrees, and my reason is sum of angles in triangle. Now I'm going to set up the sine rule again, except this time I'm looking for the side opposite C, so that's baby C. And because I'm looking for a side, I'm going to put a side at the top. I always put what I'm looking for at the top. So C over sine of the angle opposite it, which is 34,73, is going to be equal to, now you could use B over sine B, or you could use A over sine A. I'm going to use a over sine a, which is 11 over sine of 42, simply because I don't feel like dealing with decimals. And so this is a way for me to avoid that. Now I don't have to show any more working, but basically I'm going to multiply by sine of 34.73 on both sides. So it lands up being multiplied on both sides. It disappears on the left and it gets multiplied on the right. And so I get an answer of 9.365, so 9.37 centimeters. Now always just think, does that make sense? Well, if this is 34 degrees, say 34.73, but 34-ish, that's the smallest angle in the triangle, which means the smallest side must be opposite it, and 9.37 is the smallest side, so this does actually make sense. Now I just want to add a note in, so I just want to put an asterisk there and just write myself a note here, because note, because you wanted the angle, I put the angle at the top in the sine rule. So I've just written myself a little note there, because I think sometimes we make our lives difficult by not just using a sensible version. So because you were solving for an angle, we put sine of angle B at the top. And by the same logic, because in the second part we were solving for a side, we put the sides at the top. So we used the other version of the sine rule. Now gosh, I didn't really mean to write so many notes, but that's a pretty good comprehensive note on what we were thinking. So let's try another example. Right, first thing I look for, right now I only have the sine rule available to me, but I always look for a pair. There's my pair. I have an angle and I have a side opposite it. That's very good for the sine rule. Now this question says determine the length of MP, which is there, and NP, which is there. Now notice the other angle that I've been given is the 110, and so opposite is NP. So I think I'm going to solve for NP first, just because it makes sense. It doesn't really matter. So NP is the side I'm solving for. I could call it baby M, it doesn't matter. But because I'm solving for that, I'm going to put it at the top. Now the sine rule says side over sine of the angle opposite it, which is 110, would be equal to a side divided by sine of the angle opposite it. So notice you can't have a side on the top on one side and then the angle at the top on the other. It must be the same. Now basically I'm going to multiply by sine 110 on both sides, and so if I actually write that in, let me just show you, that's what I'm going to type in my calculator. We generally don't show this working, we just use our calculators, but my sine 110 cancels, and so I get NP is 21,979, so 21,98 centimeters in this case. Now again, I tend to write those in just in case it's useful for me. Now I was expecting that to be bigger than 8 centimeters, and quite a lot bigger, because this is 110 degrees and this is 20 degrees, so that angle's much smaller. Okay, now they want the length of MP. Now MP is opposite, and I don't know what it is opposite. Not a problem, because we can use sum of angles in a triangle. Now again, I wouldn't show working. I would do 180 minus 110 minus 20 on my calculator, and I get 50 degrees. And don't forget our geometry reason of sum of angles in triangle. Now I would really encourage you not to show more working than that, simply because, let me fill in my 50, in grade 8 and 9 you would show all the working on that. By the time we get to grade 11, we don't really have time for that. So definitely try and stick to doing it on your calculator, simple calculation, just working out N. Now you're looking for MP, so put MP at the top. So MP divided by sine of the angle opposite it, so that's 50, must equal, and I always pick what I know to be true. I know 8 over sine 20. My 21.98 is rounded, and so I try to stick away from that. Now what's going to happen is I'm going to multiply by sine 50 on both sides, so it disappears, and we generally don't show working. We just pick up our calculator, and I get 17,918, so 17,92 centimeters. Now that should be the middle of the range in terms of the sides in this triangle, because 50 was the middle angle in terms of sides, and 17 is indeed the middle, so that makes sense. Okay, so things you should have noticed so far: the sine was useful when you have a side and the angle opposite it. That's a starting pair, and then as long as you have one part of a second pair, you can find its partner. Right, let's look at our last question. Now this is a pretty cool question because this involves the area as well. So determine the area of triangle JKL. So we have to remember the area rule. Now don't forget the area rule is a half. Now it is technically a half AB sine C. But as I always say, there's no A's and B's in this particular question. So I don't like thinking of it A's and B's. I like thinking it as a half times side number 1 times side number 2 times sine, and this angle has to be between the two sides. So I always look for the sandwich of where is the angle between the two sides. So in this case, the only two I know is I know that and I know that so far. So if I was going to use the area rule, I would need angle L. Now I don't currently have angle L, which means I need to go and find angle L if I'm going to be using this. My second option is, since I have the 18 and I have that angle, I would need to know KJ in order to find the area. So basically I either need to find KJ and then I can use my blue sets of sides and angles, or I need to find angle L. So I've got to find something. So I always look at my opposite pair. What pair have I got? I've got 17 and his opposite 75. What other thing I've got? I've got 18, and so who's opposite 18? Angle K. So I can definitely find angle K because it's the partner to the 18. So if I'm trying to find angle K, notice I'm going to write sine of angle K as my starting point at the top. Now sine of angle K over the opposite side is over 18, and that'll be the same as sine of 75 over its opposite, which is 17. Now just as I wrote that down, I realized I'm full of typos. I'm very sorry. This was 19 centimeters when I drew it, and so I'm going to change this to 19 centimeters. My apologies. So what I would do now is I would multiply by this 18 on both sides, and so I get sine of angle K, and now I need to keep the decimals. Again, I just use a dot, 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 because then I use shift sign answer on my calculator. Now the moment I shift sign, I've got to keep in mind that there's two different answers. So my first shift sign is 66,22 degrees. Now let's look at this. Is this an obtuse angle? No, it's not. It's acute. And so this is correct because the picture is acute. And so there's no point in finding my second solution. So I'm not going to bother. Now 99 times out of 100, it's the acute solution and you don't even have to worry. Now I also know that it has to be 66.22 because 75 degrees is opposite 19. Now so far that's the biggest side in this triangle. So if 18 is smaller than 19, the angle opposite it has to be smaller than 75. So it couldn't possibly be the other option. Now how does this help me? So this is 66,22. That's wonderful. I didn't want angle K. I actually initially thought angle L would be a good idea. Now not a problem because angle L I can just find using sum of angles in a triangle. So if I do sum of angles in a triangle again, I wouldn't show any working. I would just do 180 minus 66.22 minus 75, and I get 38,78 degrees. Just don't forget your reason. Sum of angles in triangle. And now my area is easy to do because I was given the 19. Well, I wasn't because of my typo, but anyway. So it's 19 and 18, and now I know the angle in between. So the area rule is a half side times sine angle in between, which is now 38. Now this is where we kind of have to pause. Angle L wasn't the answer to the question, and therefore I shouldn't be rounding off because I shouldn't have been rounding off K and I shouldn't have been rounding off L, because otherwise I'm now going to be using a rounded off version. So let's check if that makes a difference to our answers. So if I use this rounded off version because I wasn't concentrating, I get 107,102, so 10, and this would be centimeters squared. So what I went and did is I went and redid the question, and I just kept the decimals. Now you don't have to keep all of them, but I kept 5 decimals, and notice my rounding does then change. My answer is 107,11. So basically my 107,10 is because I rounded early, and then they will penalize me for early rounding. So never round off until the final answer of a question. So this is your correct answer, simply because you should never round off. So let me just write myself a note on this. This is my correct answer, because never round off till your final answer. If they asked me, question 1.1, what is angle L, then you round off. That's absolutely fine. Then in the next question, you are allowed to use the rounded off version. But within one question, you shouldn't be rounding off. Right, so in summary, the sine rule is actually fairly nice and easy, but I've got to look for, do I know a side and its opposite angle? And then I can work on the partner of something else. Now, other than my typos and my rounding off early, I hope this has made a lot of sense. Now, what will help it make a little bit more sense